Hello, everyone. Today we're solving LeetCode problem 448. Find all numbers disappeared in an array. Let's understand the problem first. We're given an array called nums that contains n integers. All these integers are in the range from 1 to n. Some numbers appear twice in the array, and some appear only once. Our task is to find all numbers in the range from 1 to n that do not appear in the array. Let's look at the constraints. The variable n equals the length of the array nums. The value of n can be between 1 and 10 to the power of 5. Each element in nums is between 1 and n. Here's an example. The input array is 4, 3, 2, 7, 8, 2, 3, 1. The output should be 5 and 6.
Why?
Because numbers 5 and 6 are missing from the input array. Now that we understand the problem, let's explore efficient solutions. We'll cover 3 approaches with an evolution from brute force to optimal. Let's explore the brute force approach first. The idea is simple. Check each number from 1 to n in the array. Here's the algorithm. First, loop through numbers 1 to n. For each number, search the entire array to see if it exists. If the number is not found, add it to the result list. Finally, return the result list. Let's see how it works step by step. We check if 1 exists in the array. It's found. Check if 2 exists in the array. It's found. Similarly, check entire array. Our result is 5 and 6. This approach works, but notice we search the entire array for each number. That's why it has big O of n squared time complexity. Now, let's look at the Python implementation of the brute force approach. We define a function called findDisappearedNumbers that takes nums as input. We create an empty result list and get n equals the length of nums. The outer loop iterates through numbers from 1 to n. For each number, we set found to false initially. The inner loop searches if the current number exists in the array. We loop through each element in nums. If the element equals the current number, we set found to true and break out of the loop. After the complete search, if the number is not found, we add it to the result list. Finally, we return the result. Let me explain the key points. The outer loop iterates through 1 to n. The inner loop searches for the current number in the entire array. If the number is not found after the complete search, we add it to the result. This nested loop structure gives us big O of n squared time complexity. Let's analyze the complexity of the brute force approach. The time complexity is big O of n squared. Why is it big O of n squared? The outer loop runs n times, checking numbers from 1 to n. The inner loop also runs n times, searching in the array. So the total operations equal n times n, which is n squared. Let's see an example where n equals 8. To check number 1, we scan 8 elements. To check number 2, we scan 8 elements. To check number 3, we scan 8 elements. This continues for all 8 numbers. The total scans equal 8 times 8, which is 64 operations. Now for space complexity, it's big O of 1. We're only using the result array, and output doesn't count towards space complexity. We don't use any extra data structures. Here's the problem. This approach is too slow for large arrays. When n equals 10 to the power of 5, which is the maximum constraint, the brute force approach becomes inefficient. We need better solutions. Let's explore the better approach using a hash set. First, let's understand the problem with brute force. Searching for each number takes big O of n time, which makes it inefficient. The solution is to use a hash set for big O of 1 lookup instead of big O of n scanning. Here's the evolution from brute force. In the brute force approach, for each number, we scan the entire array, which takes big O of n per check. With the hash set approach, for each number, we check in the set, which takes big O of 1 per check. This is a huge improvement. Here's the algorithm. Step 1. Create a hash set and add all elements from the array. Step 2. Loop through numbers 1 to n. Step 3. Check if each number exists in the hash set. This is big O of 1 lookup. Step 4. If the number is not in the set, add it to the result list. Step 5. Return the result list. Let's see how it works with the array 4, 3, 2, 7, 8, 2, 3, 1. Step 1. We create a set containing 1, 2, 3, 4, 7, 8. Notice duplicates are automatically removed. Step 2. We check each number in big O of 1 time. Is 5 in the set? No, so we add it to the result. Is 6 in the set? No, we add it to the result too. Our result is 5 and 6. The key improvement is big O of 1 lookup time using the hash set. Now, let's look at the Python code for the better approach using a hash set. We define the function findDisappearedNumbers. In step 1, we create a set of all elements using setOfNums. This converts the array to a hash set. We create an empty result list and get n equals the length of nums. In step 2, we check each number from 1 to n. For each number, we use the condition, if number not in number_set. If the number is not in the set, we add it to the result list. Finally, we return the result. Let me explain the key improvements. The statement setOfNums creates a hash set from the array in big O of n time. The lookup operation, number not in number_set, is big O of 1 because hash set lookup is constant time. The loop runs n times with big O of 1 lookup each time. This is much faster than the brute force approach. However, there's a trade-off. This approach uses extra space for the set. Let's analyze the complexity of the better approach using a hash set. The time complexity is big O of n. Why is it big O of n? Creating the set from the array takes big O of n time. Looping from 1 to n takes big O of n time. The hash set lookup is big O of 1 per operation. So the total is big O of n plus big O of n, which equals big O of n. Let's see an example where n equals 8. Creating the set takes 8 operations. Checking 8 numbers takes 8 operations. The total is 16 operations. This is much better than 64 operations in the brute force approach. Now for space complexity, it's big O of n. The hash set stores all unique elements. In the worst case, all n elements are unique. So the extra space used is n elements. Here's the improvement. This approach is fast but uses extra memory. This brings us to an important question. Can we achieve big O of n time complexity with big O of 1 space complexity? Yes, we can. Let's explore the optimal solution next. Let's understand the evolution. The hash set tracks which numbers exist, but it uses extra space. Can we track which numbers exist in the array itself? Yes, we can. Here's the trick. Array values are from 1 to n. Array indices are from 0 to n-1. When we see a number, we mark that position in the array. The marking method is simple. Make the value at that index negative. How does marking work? A negative value means this number exists, just like a hash set contains it. A positive value means this number is missing, like the hash set doesn't have it. Let's see a simple example with the array 1, 1. We see number 1. We mark position 1-1, which is 0, as negative. The array becomes -1, 1. Position 1 is still positive, which means number 2 is missing. Here's the key insight. The array itself becomes our hash set using negative marking. This eliminates the need for extra space. Let's see the optimal approach step by step. We start with the array 4, 3, 2, 7, 8, 2, 3, 1. I'm also showing memory addresses for visualization purposes. Here's the initial state. Index 0 through 7 contains values 4, 3, 2, 7, 8, 2, 3, 1. The memory addresses are 100, 104, 108, 112, 116, 120, 124, and 128. Now, let's begin this step-by-step marking process. We see the first element, which is 4. Number 4 maps to index 3, which is 4 minus 1. So we mark index 3 as negative. The value at index 3 was 7, and now it becomes minus 7. Next, we see element 3. Number 3 maps to index 2, which is 3 minus 1. We mark index 2 as negative. The value at index 2 is 2, and now it becomes minus 2. Then we see element 2. Number 2 maps to index 1, which is 2 minus 1. We mark index 1 as negative. The value at index 1 was 3, and now it becomes minus 3. We see element 7. Number 7 maps to index 6, which is 7 minus 1. We mark index 6 as negative. The value at index 6 was 3, and now it becomes minus 3. Next, we see element 8. Number 8 maps to index 7, which is 8 minus 1. We mark index 7 as negative. The value at index 7 was 1, and now it becomes minus 1. Now we see element 2 again. This is a duplicate. Number 2 maps to index 1, which is 2 minus 1. But index 1 is already negative, so we skip this step. The array remains unchanged. We see element 3 again. This is also a duplicate. Number 3 maps to index 2, which is 3 minus 1. Index 2 is already negative, so we skip this step too. The array remains unchanged. Finally, we see element 1. Number 1 maps to index 0, which is 1 minus 1. We mark index 0 as negative. The value at index 0 was 4, and now it becomes minus 4. Now, let's find the missing numbers from our final marked array. Here's the final marked array. Index 0 through 7 has values minus 4, minus 3, minus 2, minus 7, 8, 2, minus 3, and minus 1. To find missing numbers, we loop through each index and check if the value is positive. Index 4 has value 8, which is positive. This means number 5 is missing. Index 5 has value 2, which is positive. This means number 6 is missing. So our result is 5 and 6. Remember the rule: if index I has a positive value, then number I plus 1 is missing. This is how we identify the missing numbers. Now, let's look at the Python code for the optimal approach. The core idea is to use the array itself as a checklist by marking with negatives. Here are the algorithm steps. Step 1. Loop through the array. Step 2. For each number, calculate the target index equals absolute value of number minus 1. Step 3. Mark the value at the target index as negative. Step 4. Loop through the array again. Step 5. If the value at index I is positive, then I plus 1 is a missing number. Now, let's see the Python implementation. We define the function findDisappearedNumbers. We get n equals the length of nums. Steps 1 through 3 mark indices as negative. We loop through the array using I from 0 to n. For each element, we calculate index equals absolute value of nums at I minus 1. This gets the target index. If the value at nums at index is positive, meaning it's not already marked, we mark it as negative by setting nums at index equals negative nums at index. Steps 4 through 5 find positive indices. We create an empty result list. We loop through the array again. If nums at I is greater than 0, meaning it's positive, we add I plus 1 to the result, because I plus 1 is the missing number. Finally, we return the result. Remember the key mapping: number x maps to index x minus 1, and we mark it negative. Let's analyze the complexity of the optimal approach. The time complexity is big O of n. Why is it big O of n? The first loop, which marks indices, is big O of n because it visits each element once. The second loop, which finds missing numbers, is also big O of n because it visits each index once. The total is big O of n plus big O of n, which equals big O of n. Let's see an example where n equals 8. The first pass takes 8 operations for marking. The second pass takes 8 operations for finding missing numbers. The total is 16 operations. Now for space complexity, it's big O of 1. We don't use any extra data structures. The array is modified in place. We only use the result array, and remember, output doesn't count in space complexity analysis. This is the best approach. The time complexity is big O of n. The space complexity is big O of 1. This solution demonstrates optimal thinking by achieving linear time with constant space. Let's summarize everything with a comparison of all 3 approaches. Here's the comparison table. Brute force has big O of n squared time and big O of 1 space. The trade-off is that it's too slow due to repeated scanning. Hashset has big O of n time and big O of n space. It's fast but needs extra space. Index marking has big O of n time and big O of 1 space. This is optimal because it's fast and uses no extra space. Here's a pattern to recognize. When an array contains a range from 1 to n, think about index mapping. This is a powerful technique. Thank you so much for watching this tutorial. I hope you found this lesson helpful and easy to understand. If you enjoyed this video, please hit the like button. It really helps the channel grow. Don't forget to subscribe to the channel for more beginner-friendly programming tutorials and helpful tips. Feel free to comment your questions or thoughts below. I love hearing from you, and I try to respond to every comment. And don't forget to hit the bell icon so you get notified whenever I upload new videos. See you in the next lesson.